Okay, now I keep saying from the left and from the right. We have a fancy way of writing that. This notation right here means you've got yourself some function. You want to know what's happening at the point x equals a, but you want to know what's happening as you approach from the left-hand side. That little negative there is mathematical notation, meaning from the negative direction. Nothing is negative here. This means from the left, and a little plus means from the right. So let's look at some examples here. These same examples from above. So we're looking at g of x here. This notation right here says you got your function g. That's how I know to use this one, because it says g. I want you to look near x equals 2, not negative 2. That negative does not mean anybody's negative. Look at x equals 2 right here, and look just a little tiny bit below 2, to the left of 2. That's what that negative means, just a little tiny bit to the left of 2. What are your y values close to? Well, they're all the same. They're all -1. But this notation says same function, g of x. Look near x equals 2, but that plus there means just a little bit above 2. So here's x equals 2, a little above 2. I'm up here. I'm on this part of the graph. And now I want to approach downward. I want to go this way and get closer and closer from above. What are these y values getting closer to? Well, they're all the same. All of these y values are +1. So we call these one-sided limits. These one-sided limits both exist. The limit as x approaches 2 from the left is -1. From the right is +1. It has been decided that when we just ask, what is the limit? What's the whole function doing? We've decided as mathematicians that that means what's it doing from both sides. So we say that a limit exists if and only if 2 things happen, 3 things happen. Both one-sided limits exist, and they're the same thing. I'm going to repeat that. The limit is f of x as x approaches a equals L, if and only if both one-sided limits exist, they both approach a number, and it's the same number from both sides. So in this graph, when I approach from the left, all my y values are getting closer to, what was that, 1, 2, 4. When I approach from the right, all my y values are getting closer and closer to 4. The left-handed limit, the right-handed limit, they're both 4. Therefore, the limit exists and is 4. In this graph, it's this information right here. Both one-sided limits exist, but they're 2 different numbers. That limit then does not exist. So the limit of g of x as x just approaches 2 without the little negative or the plus would not exist. Okay. So we could maybe type this into our function real quick. So this is like the other guy that we had, but now he's got an absolute value in it. Okay, so let's see if we can. think you got to go. I'm just going to start over. To do absolute value, I always find the easiest just to go into catalog. So second, catalog, absolute value. Oh, I wasn't. I was on the equal sign. Sorry. Second, catalog, absolute value of x squared minus 4. Get out of my absolute value divided by x minus 2. And I need parentheses here. We can take a look at the graph. I have no idea what kind of window I'm on here. Maybe I should go to a standard window. Oh, that's weird looking. Like we can kind of look at the graph here and say, I don't even need to do a table of values. As x is approaching 2 from the left. So now I'm looking at this chunk of the graph below x equals 2. These y values are approaching 1, 2, 3, -4. As I approach from the right, this question right here. So think of that as 2 plus a little bit. Think of this one as 2 minus a tiny little bit. So I'm still trying to get to x equals 2, but now I'm above 2. What are these y values approaching? +4. I could see the same thing if I were to go here into the table. So I would do table set. I want to be near 2. So maybe I would do 1.5 as my starting and go by, it will go by 0.2s so that we can do above and below. And then go to table. So these y values below, see here, all these x values are less than 2. Y values look to me like they're getting closer to -4. Now I'm above 2 from here down. As I'm going smaller, getting closer to 2 from above, the y values are getting closer to +4. So this one seems to be -4. This one seems to be +4. That means the limit as x approaches 2 of the function does not exist. The actual limit only exists if 3 things happen. Both one-sided limits have to both exist and they have to be the same number. They weren't the same number, so that limit doesn't exist. Okay, now I really like these problems. We get a piecewise function. So this is one of those things from college algebra. Piecewise, remember those? You were supposed to know how to do all these. You're supposed to know how to graph piecewise functions. Let's graph this guy. Now there are ways to type in piecewise functions into a graphing calculator, but I've always found it more of a pain than it's worth. We know how to graph this guy. Come on. Let's graph the top one. Y equals x plus 1. It's a line. The y-intercept is the point 0, 1. My slope is 1, so if I go over 1, up 1, there's another point. Here's the graph of that line. Oh, I totally missed. Oh, but I don't want the whole line. I only want x less than 2. This is the way I found easiest to graph piecewise functions, is graph the whole thing and then erase the part you don't want. I only want this from x equals 2 and over to the left of 2. Okay, so I just want this chunk down here. Oh, that is so ugly. I just want this. I'm going to erase the part I don't want. Okay, what about this other guy? X squared minus 4. I know how to graph that. That's just regular old x squared scooted down 4. So 1, 2, 3, 4. The entire graph would look like this. But I don't want the whole thing. I only want x is bigger than 2. Here's x equals 2. I only want this chunk of it from here, from right there over. So that's this piece right here. So keep the part we want, erase the part we don't want. Now we got to fill in our endpoints. Who gets the solid dot? The one with the equal to gets the solid dot. So we got to figure out what's that y value that goes with this. Well, if I plug in, oh, my graph was very poor, wasn't it? Let's see. Looks like my graph was way wider than it should have been. And sometimes you got to do that when you're graphing piecewise functions. If I plug in a 2 here, 2 squared is 4 minus 4 is 0. This shouldn't be way down here. This should have been here. So I really want, I'm kind of adjusting that there. This should have looked more like this. And so let's get rid of this stuff here. That was just a guide to help us. And he gets the solid dot because he has the equal to. Okay, what about this open circle? This guy's supposed to have an open circle. We got to figure out where that's supposed to be. So we plug in this x value there. 2 plus 1 is 3. So that right there is supposed to be up at 3. And he's supposed to have an open circle. So that's what this graph would look like. That's college algebra. That's all I've done here. Now we can answer these questions based on this picture. This says I'm near 2 and just a little bit below 2. What's the y value approaching? I don't care what it actually is. What's it approaching? Just making sure this looks like this one's an open circle. That's close. But that's when I'm down here. I'm on this one. I'm below 2. Here's 2. I'm getting closer and closer to, as I get closer to 2, 3. What about this one? Now I'm a little bit above 2. What are my y values getting closer and closer to as I get closer to 2 from above? I have to stay above. That's what plus means, above. Negative means below, plus means above. I'm getting closer to 0. Now, what if I asked what is f of 2? This says, where's the solid dot? Where's the actual function value? That's that one right there. That's 0. What if I asked, what's the limit as x approaches 2 of f of x? A limit exists if and only if both one-sided limits exist, they do, and they agree. They don't. This limit does not exist.